Okay, hello everybody. Welcome back, and let's move on. We're trying to get through this chapter on probability, and I want to talk today about conditional probability ultimately. And to lead into that, let's start thinking about what happens in a situation where I have some kind of probability experiment, and I have two events, and the likelihood of one of the events changes if I assume that the other event already happened. So what do I mean? Let's think about a nice easy example with a deck of cards down here. And what I'm going to do is I'm going to have two cards be drawn from my deck. And the second card that will be drawn from the deck without putting the first card back in. So I'm going to fan out my cards. I'm going to have somebody pull a card. And I'm going to have somebody else pull a different card without putting that first card back in. So here's my question I want you to think about to start. Two cards are drawn from a deck and the first card is not replaced. What is the probability that the second card that gets pulled will be hearts if I assume that the first card was a heart? So I fanned out my deck. I said somebody pull a card, pull any card, and we're going to assume that that first card was hearts. Now what's the probability that the second card will also be hearts? Think about that for a second before you listen to the answer. Try to come up with the right probability. What did you come up with? What did you think it was? Well, if we think about it hard and we try to visualize this, then we can imagine a case where I have my usual deck of 52 cards, and over here on the left, if we look at this picture, we see a full deck of cards, but we're going to assume that the first card that was drawn was hearts. So there's actually one heart missing. Notice that I deleted the ace of hearts here. It doesn't particularly matter which card was picked, but we know it was a heart. So if that heart is drawn and not replaced, then if I asked you to close your eyes and draw from this deck here on the left, I said pick a card, any card, what's the likelihood that you get a heart? Well, if I just think about my old-fashioned rules on probability, I look at this entire collection of cards here and I know that I have, 51 cards. Not 52, because one of the hearts is missing, right? This is already in the hands of whoever drew the first card. And out of those 51 cards, how many of them happen to correspond to hearts? Well, the answer is 12. 12 out of 51. So the probability that somebody will pull a heart on the second card, given the assumption that a heart had already been pulled, is 12 out of 51. Similarly, you could look at the second question. If the first card was a spade, now what's the probability that the second card that's drawn will be a heart? And you can look at the same sort of situation and say, well, if the first card was actually a spade, then I'm still going to be drawing from a deck on my second pull with 51 cards in it. And out of these 51 cards, how many of them correspond to hearts? Well, the answer is 13, because now I have my full collection of 13 hearts in the deck, the remaining deck, but I'm missing one spade. So if that first card was a spade rather than a heart, then my probability of pulling hearts on the second card is actually 13 out of 51. So what's the real point here? The real point is that if I look at this, the probability of getting hearts on the second card, 13 out of 51, it's fairly close to 1 over 4, but it's not equal to 1 over 4. And similarly, the probability of me getting hearts on the second card when I assumed that the first card was hearts is 12 out of 51, and 12 out of 51, this is not equal to 1 over 4 either, right? They're somewhat close, they're fairly close, but it's not 1 out of 4. My probability of getting hearts has changed when I assumed that one of these two events has happened, that the first card was either hearts or the first card was spades. In both cases, it changed the likelihood of me getting a heart on the second card, because if I don't make any assumption, and I just say we're going to pull two cards from a deck, what's the probability that the second card is hearts? Then that probability by itself is 1 out of 4. But once I add in these second events and I assume that they have occurred, I'm assuming that the first card is hearts or the first card is spades, then my likelihood of getting that heart on the second card has changed. So what we're considering here is what's called a conditional probability. Okay? I don't want to talk about this stuff now. I should have just said what probability. And so what we're actually considering here is what's called a conditional probability. I have some event that I want to consider, and that's the event that the second card is hearts. And I'm not considering it just by itself. I'm considering it with a second event that I'm assuming has already happened. So in our example, I'm trying to consider what's the probability that the second card is hearts, and we've done assumptions that either an event that the first card was hearts or the first card was spades had already occurred. These are two separate events, right? I could separately have asked you, what's the probability that the second card is hearts? Or I could have asked you, what's the probability that the first card is hearts or spades, etc., etc. So when I consider the probability that some event will occur, given the assumption that some other event has already occurred, this is what's called a conditional probability. And we use this notation here to denote it, the probability of B given A. So the way you read this is you look at this, P bracket means probability or the probability of the event B happening, and then this vertical line here should be replaced with the word given when you read this out loud. The probability that B happens given that A happens. And that's what we call a conditional probability. So the example we just saw was if A is the event that I draw hearts on the first card and B is the event that I draw hearts on the second card, then this notation means what's the probability of B given A, or what's the probability that I draw hearts on the second card given the assumption that I already drew a heart on the first card. And what's that probability? Well, we just saw that's equal to 12 out of 51. So I would read this as a probability of B given A is 12 out of 51. And similarly, if I take B to still be the event that I draw hearts on the second card and C be the event that I draw spades on the first card, then I would read the probability of B given C as, well, what is this in my head? Whenever you do a probability question, make sure that you get an intuitive grasp of what the question is asking first, right? Don't try to look for short answers, solutions, formulas, nothing like that. Think about what's really being asked here. And if you see this with these two descriptions of the events, then what's being asked of you is, what's the probability that you will draw hearts on the second card of this experiment if we assume that you drew a spade on the first card? And what we saw is if you draw a spade on the first card, then you still have 13 hearts in the deck and there's only 51 cards left, which is why this answer is the probability to B given C was 13 out of 51. We already saw this answer. This is just me writing it with this new conditional probability notation. Okay, so let's do a quick example here of a conditional probability. And again, we're going to think about this without introducing the conditional notation for a moment, just to emphasize how this works. So we're going to refer back to this table down here on the bottom left that shows a listing of a whole bunch of accidents. I think there was 985, if I remember right, fatal traffic accidents. And this left here column lists which of those accidents involved an intoxicated pedestrian. The right column is which accidents involved a non-intoxicated pedestrian, and the first and second rows indicate when the driver was intoxicated, respectively. So my question is, what is the probability that the pedestrian was intoxicated if we assume that the driver was intoxicated? And so think about what this means. I'm saying we're assuming that the driver was intoxicated. So in particular, I don't care about any of these accidents that involves a driver that was not intoxicated. We are assuming the driver was intoxicated. This means we can take this as a absolute truth in this question. The driver was drunk. What is the probability that the pedestrian was drunk if these are the only accidents we care about? Effectively, this assumption has reduced our sample space from 985 to just this top row, to just 59 plus 79. That is all that we care about now, is these, 138 accidents. So if my sample space is only these 138 accidents, if I'm assuming that the driver was intoxicated, what is the probability that if I picked randomly from these top two, this top row, these top two values here, what is the probability that if I picked from these 138 accidents that the driver was intoxicated? Well, out of these accidents, only 59 times was the pedestrian actually intoxicated. So, in this case, out of these 138 accidents, 59 times the pedestrian was intoxicated. So the probability of the pedestrian being intoxicated, given the assumption that the driver was intoxicated, is 0.43 or 43%. I can read this by saying something like 43% of the time the driver was drunk, the pedestrian was also drunk. Think about how easy that sentence is to understand. 43% of the time that the driver was drunk, the pedestrian was also drunk. And that's exactly what this means, right? And these are nice interpretations of this data that you need to be able to make when you're analyzing some large set of data. So one more quick example on this conditional probability, and then I'll close it off, and I'll do one more video talking about dependence in events. So let's suppose that I have a class, and there's 27 students in that class, and I have 25 of 27 students who are female. Seems a bit disproportionate, but this was actually my stats class last year. This was the real proportion of it. And furthermore, you know that 12 of the 27 students are CSM majors, right? They're in science or mathematics. And out of those 12 students, one of those students is a male. So here's my question for you. Think about it, work through this data a little bit, and try to get a grasp on it. I'm going to ask you that if I randomly select a student in my class, what is the probability that that student will be a male, given that they are a CSM student? Think about what that means. That means that I've picked a student, I'm going to assume that they're CSM. What's the probability that they are also a male? Think about it for 10 seconds, and then I'll give you the answer. Okay, so what should we do for this? You might be a little bit confused, maybe not, but let me give you a hint. One way that you can always try to approach this problem is really first understand your sample here and understand what it looks like visually somehow. So one approach to here is I have a whole bunch of different pieces of information. So what I can do is I could try to sort my class distribution into those students that are male, female, and CSM, and not CSM. That's all I really care about for this particular question. So here's my question. If I asked you to fill in the 27 students in my class into this table, could you do it based on this information? Now give that a try before I take one more step. If you're totally stuck, try to fill in that table first. How many of students in my class are male? How many are female? Of those males, which are in CSM? Which are not in CSM? See if you can fill this in first, and then I'll fill it in for you. Okay, so here's how I'll fill this in. I just need to reason my way through it a little bit. Let me look at this last sentence, and I know that, what do I have? I have 12 students in CSM, so I should get a total of 12 down this first column. And out of those 12 students, I know that only one of them is male, so that tells me I only have one male who's in CSM. And I have 11, therefore, females in CSM. And so, what else do I know? Well, how many total males do I have? Well, I have, 27 students and 25 females and 2 males. So now it's very easy for me to fill in the rest. There's only 2 males in this class, so my total males has to be the sum of this first row. And I have 25 females, so if 11 of them are in CSM, then that means 14 of them are non-CSM majors. So there we go. This is what my class distribution looks like. It's just a simple step to fill it in. And now my question is, suppose that we've randomly selected a student. What is the probability that that student will be male given that they are in CSM? So what I'm looking for is the probability that they're in male, a male, given that they're in CSM. Where here, of course, M denotes the event that I'm picking a male, and C is the event that I pick somebody in CSM. So the probability that I pick a male given that they're in CSM, now I'm assuming that they're a CSM major. So I effectively just eliminate everybody who's not in CSM. Assuming that it was a CSM student that I picked, the probability that they're a male, well, I have one male out of how many total CSM people? 11 plus 1, or 12. So the probability that I select a male, assuming that the person I selected was in CSM, is just 1 out of 12. And if I look at this question and think about the demographics of this class, it's not hard to see why this is true. Assuming that I pick somebody in CSM, it's only 12 people in CSM. One of them is male. So the probability that I pick somebody in CSM, assuming they're a male, is 1 of 12. 12 CSMs, 1 male, probability is 1 out of 12. Any of these conditional probabilities basically amounts to just reducing your sample space to some size that you're trying to consider. And this is something you do in data a lot. I have a big, wide collection of data. Sometimes I only want to consider the male portion of it. Sometimes I only want to consider the females. If I'm studying GPAs, maybe I only want to consider the high GPAs, the low GPAs, whatever it is, right? Reducing our sample space is a common way of analyzing our data, and when we do that, all we're really doing is